Okay. So our eventual goal this time is to actually figure out what the atom's really like. Okay? So, and we've got part of it down already. The part we have down is the nucleus. Well, we've learned everything we're going to learn about the nucleus and how it changes. Okay. This unit is going to focus on the electrons, because we haven't said where the electrons are very specifically yet. Right? So as we're going through history, we've talked about how the models have developed, and our last model, the one we're at our baseline at, is Rutherford. Rutherford's model is the last one on our list that we've done so far. Okay. And Rutherford discovered that small, dense, positive nucleus in the middle of the atom. Right? I'm not changing that. And our small, dense, positive nucleus we now know is made up of protons and neutrons in a certain ratio, and on very rare occasions they fall apart. Here. And we can describe how they fall apart with equations, but that's what we've learned about protons and neutrons. We're not going to talk about atoms changing into other atoms ever again this year. Nuclear is strange. We taught you the strange stuff first. Okay? Now we're going to talk about atoms, and then you're going to find out that atoms are a little bit stranger than you thought they were too. Okay. So where did Rutherford say the electrons were? Where were the electrons? He said outside the nucleus in this area called the electron cloud. He didn't say specifically where the electrons were. All he said was that they were outside the nucleus in a big area where you're going to have a chance of finding the electron. It is not a cloud of electrons. This has got a whole bunch of electrons here, so it looks like I got a cloud of electrons. No, it's where those electrons can have the yellow. Those electrons can have a chance of being found anywhere in that yellow spot. I just drew some in right now. Here's the indication that it's not a cloud of electrons. Hydrogen has an electron cloud. Hydrogen only has one electron. So if you only have one electron, can it be the cloud? So what it's a cloud of is a cloud of probability, a cloud of chance. Okay? Where you have a chance of finding it. Where there's a good, where the odds are that this is where the electron is going to be found. That idea is going to go away for a while, and then it's going to come back. So Thomson, while he was doing his experiments with the cathode ray tube, had a student named Rutherford. Rutherford graduated, got his own lab. He had a student named Niels Bohr. Niels Bohr. And he asked a pretty simple question. It's the opposite of my second Bellwork question today. Okay. Why doesn't the electron fly away from the nucleus? Why doesn't it? Well, it's about charge, yeah. What charge does the electron have? Negative. What charge does the nucleus have? Positive. How do opposites affect each other? They attract. So the reason why the nucleus doesn't fly off into space is because opposites attract. But actually, the harder question is the opposite of that. If their opposites attract, how come the electron doesn't fall into the nucleus? They're right next to each other. You got the positive piece, a negative piece right next to each other, and the electron should just go straight to the nucleus. Does that seem logical and reasonable? If opposites attract, I got opposites right next to each other, they should be attracted to each other and should fall in. had to come up with a reason how you could be attracted but not collide. And Bohr said, hey, here's what's going on. The electron doesn't fall into the nucleus for the same reason the Earth doesn't fall into the sun. And the moon doesn't fall into the Earth. Because it's moving in circles. And so it's not always obvious to see why moving in circles keeps you from falling together. So I'll try to give you a thought experiment, the way that Einstein did it. Okay, so if you throw a ball, its path is a curve and eventually hit the ground, right? But if you throw downhill, if the ground slopes away from you, that ball is going to travel further before it hits the ground. Everybody agree? Okay, pretty logical stuff, right? Okay, now, this is you on top of the world. As you throw the ball straight out, it's going to start to fall, but notice, if you're throwing fast enough that you can see the curvature of the Earth, that the Earth curves away just like it was a hill. And the ball's going to go a little bit further because the Earth curves out of its way. And if I throw it faster, it'll go further before it hits the Earth. And if I throw it fast enough, it'll hit me in the back of the head. Because it'll keep falling at the Earth, but it'll fall just as fast as the Earth curves away. So it keeps falling, continuously missing. That is what orbiting is. The moon is falling towards the Earth all the time. It just keeps missing because the Earth keeps moving out of the way. Does that make sense? Same thing with the sun. The Earth is going around the sun. It's falling towards the sun. It's just that it goes so fast this way that it's not over that part of the sun anymore. It's curved off, so it drops down some without getting any closer. Because the sun is curved away, the Earth can come in and still be the same distance. So that's how going around in circles keeps things from falling together. Okay. So that's why I said like moving like planets around the sun. Sometimes it's called the planetary model. Okay. So they move in circular orbits at different levels. Oh, just so you know, nobody's misled. Bohr was wrong. Okay. We're going to have to fix. We're still not. Bohr is not the ultimate model. Okay. But what separated one part from the next was the amount of energy. You had electrons at this level, then electrons at this level, and the difference was one had more energy than the others. Okay, so when you see a picture of an atom, oftentimes they draw it like that. Okay, well, they show the ring. You can't always tell what they're trying to draw as 3D rings because there's actually two layers of electrons and they go around. Okay, you're getting sleepy. No. So you see that the inside ones are going around versus the outside ones. Okay? So two different levels of electrons. Hey. How did he know that there were levels of electrons? What was he trying to explain with his levels of electrons? Because remember, that's what he's trying to do. That model is still a theory. He's trying to explain something. And I want to show you what he's trying to explain. So up here on my counter, I have got 6 dishes. Okay. The first one I didn't put anything in, and I'm going to pour some alcohol into that. The second one, I've got sodium chloride, some table salt. I'm going to put some alcohol in that. The third one has got strontium chloride. Fourth one has copper chloride. Fifth one has lithium chloride. And the last one has potassium chloride. Okay, and then I'm going to take the alcohol and put it over here. Okay, I need you, everybody, it would be dangerous to stand up now, so please, nobody get up, because every year chemistry teachers do this experiment and burn up their classes. Yeah, usually just the people in the front row. Now, okay, I've set up so if you're, as long as you're in your chair, you're not going to get hurt. Okay? Okay, so first, the blue. This blue right here is the color of methanol burning. Okay, it burns like this blue, and you can't see it in daylight. This is what they use in IndyCar racing and NASCAR as fuel, and you can't see it when people are on fire. That's why I had to turn off the lights. The yellow is the color of flame you're used to seeing, and that's sodium. Sodium always makes a yellow flame. So when you're watching something burning and it's giving off yellow, that means the sodium atoms, that there are sodium atoms in there. Okay? The green, things with copper atoms give off green light. Okay? The red, it's lithium over here. Red. Lithium always gives off red light, but so does strontium. Strontium also gives off red, but they're not the same red. This one's got more orangey than that one. That one's got more purple. Right? It's hard to see in the last one, but potassium gives out like a lilac, a light violet. It's hard to see in this bright room. And there's a little bit of sodium in there because we're seeing some yellow. It's hard to get rid of sodium. Sodium gets into everything. That's why everything burns yellow. Okay, so this is what Bohr is trying to explain. The only thing different about these dishes is what metal was in the compound I put. They were all chlorides: sodium chloride, strontium chloride, lithium chloride, copper chloride. They're all chlorides. The only difference was the metal. So whatever is causing the difference has got to be because they're different kinds of atoms. There's got to be something different in the atom structure that gives them different colors of lights. See how that's a logical outcome of this? Okay. So he's trying to figure out why they gave off the colors of light they did. And our current model the atom did not explain that. It doesn't explain any of that. So that's what Bohr is trying to explain. And that's how he knew that there were energy levels. I'll get this here and we'll go back to it. So it's hard to explain in circles. Okay, so I'm going to take my circle and make it flat by turning it into a ladder. So rather than layers of circles, I'm looking straight up and just seeing like it would be a ladder, one place after the other. Okay, so the Bohr model is like a ladder in some ways. Okay. The nucleus is down here at the bottom. And the further I go up, the more energy I have. Just like on a ladder, if I fell off the first step, I would hurt myself a lot less than if I fell off the 5th step. That the higher I go on the ladder, the more energy I have. Well, that's what the energy in the energy levels for Bohr's atom. The further away from the nucleus you get, the more energy you have. Further away from the nucleus, more energy. So this is what Bohr said was happening in our dishes. He said, electron starts off on a step. When you heat it up, you put energy into it so it jumps up some steps. Because you put some energy in, it gets more energy by going up. It's not stable up there. So it falls down the ladder back to where it started. And when it falls back down, it's got to get rid of that energy, and it gets rid of that energy as light. That the heat makes it move up, but when it falls back down, it gives it off not as heat, but as light. So the color of light we see is based on which step it fell from. That if it falls from a higher step, it's going to have a light of higher energy. If it falls from a lower step, it's going to have light of lower energy. So it explains why it gives off light. But here's where the ladder's a bad example. If I climb a ladder and I'm going from the first step to the second step, and halfway up somebody pushes me, I am going to fall from the first and a half step. And I'm going to hurt myself more than the first, but less than the second. Everybody agree that's what's going to happen to you? You climb up a ladder and somebody pushes you off. You can be halfway up a step. The electron, I drew it wrong last time. I showed it moving. No, the electron disappears off the first step, shows up on the fourth step. It is never in between those two places. It goes from the first step to the second step without ever being in between those two places. And how do they know that it's never in between those two places? Because of the light. Because if the jump from here to here gives me green light, right? If I made it just short, I should get a color that's just a little less energy than green. But I never get that color. The electron's never there. Because if the electron can be there, it can fall from there. And I'll get to see that color light. But it can't be there. The electron can never be between energy levels. It's on that level or it's not on that level. And that's different than us going up a ladder. I can be halfway between steps. The electron is never in between. It leaves this one, shows up there. Does that sound bizarre? It is. It's the first of the bizarreness, but it's the truth. It's what happens. It stops being at the first energy level and starts being at the fourth and is never in between any of them. Okay. Atoms behave in bizarre ways that we don't experience, so we're just going to have to figure out how they work and trust that the explanation works. Because it's not going to be like things we can see. I don't get to go to the top of the ladder by just blinking from the bottom to the top. I got to work my way all the way up there. Right? So, those colors are how he knew that there were energy levels. Because he got the specific colors from the specific atoms. And he never got a color that was close. He got this color or he got nothing. Okay? Make sense? Okay. Sorry, hey, but hey. So, in order to understand this, we're going to have to talk about color. Because we don't know very much about color. You haven't learned. I could have asked you a really mean Bellwork question. What is color? There's got to be something behind the different colors. What is it? Okay, we're about to learn what's behind it. Okay, and the way you learn about light is you tear it apart. And one of the devices you can use is a triangular shaped piece of glass called a prism. Okay. And when you pass white light through it, it separates it into the whole rainbow. Okay. That rainbow is called the spectrum. Well, it's called the visible spectrum because we can see it. Spectrum just means a wide range. Now, another way you can do it, other place you see rainbows is if you get a whole bunch of thinly spaced lines. Individual lines really close together. We'll learn later why it works, but if you have a whole bunch of individually scratched lines on a reflective surface, like on the back of a CD, you see the rainbow on the back of the CD, that's because there's a whole bunch of individually scratched lines in there. We'll learn later actually why it makes a rainbow, but it also makes the rainbow. So I can either use a triangular piece of glass or scratched lines to see the whole rainbow. Okay with that? So I'll see the whole rainbow either way. Anyway, that's what white light will do. But if I took the light from those flames, if I heat up an element, or later on you'll see me do it, pass electricity through it and get it to glow, like a neon bulb. A neon light, you pass electricity through it, it glows. So today you saw the heat making a colors. I'll show you the making colors the other way next week. We're going to look at color a lot in the next week. So if we were to take that purplish red light from lithium, we saw just a minute ago, and pass it through the prism, you wouldn't get a whole rainbow. You get something that looked like that, where you wouldn't be able to see the black. All you would see would be the rays of red, blue, and purple. Because that color we see as a whole is really made by those three colors. Black is the absence of light, white is all the lights. And black lights are wavelengths we can't see. So they look black to us. To a bee, it'd be like a spotlight. Okay, and as you saw, each element gives off its own characteristic colors. I can tell if there's copper in something by doing that and see if it gives off the lines that copper gives off. If it gives off the colors that copper gives off, it's got copper in it. So if I heat it up and make it glow, I can use that to figure out what stuff is. It can be used to identify the atom. In fact, one of the elements, helium, was known about before they ever found it. Okay? So what they did was they took the light from the sun and they passed it through a prism and looked. And there, you looked at it and it made lines like this. And there were lines that did not match up with any known element on Earth. There were lines for the other elements on Earth because they're in trace amounts on the sun, so you're going to see little tiny lines for them. But there were lines that didn't match up to any element, which told them there must be an element we don't know about. And since that element is found on the sun, we will name it after the sun. Helium. So helium is named after Helios, the Latin name for god of the sun. Okay? So they knew about it, they named it before they ever found it on Earth. Because remember, once helium gets to the surface of Earth, it leaves. So there's none on the surface unless you catch it. Okay? But that's how we know what stars are made out of. I mean, if you want to figure out what the nearest star is made out of, you're not going to be able to go get a bucket of star and test the stuff because it's too far away and it's a tad bit warm. Right? So we're not going to be able, so we can't go get a bucket of star and see what it's made out of. So what we do is we look at the light that it gives off. And that light, when you break it up, makes lines. It's going to make a bunch of lines because it's got a bunch of elements in it. And from where the lines are at, you know what elements there are. And by how bright the lines are, you know how much there is. That if you got more of it, you're going to make more of that light, so that line's going to be brighter. So you can tell not just what element there is, but how much of it, based on where the lines are and how bright they are. Because that's how you know what stars are made out of, because the light they give off. So what you see when you look, is you see something that looks like that. You see a strip where it's a rainbow, where most of the colors have been removed. Notice they're still in rainbow order. We haven't changed the order. All we've got is just individual colors instead of all the colors of the rainbow, where the colors are in a line. This is called a line spectra. Spectra is singular. Spectra is plural. Spectrum is singular. Okay. These are line spectra because the colors come in line. And these are unique to each element. Every element has its own set of lines. Okay, these are the emission spectra. This is the light given off. The exact opposite of this, so if you took white light and shined it through the gas of this element, you would get the opposite image. That means every place where it's black, there would be that color of the rainbow, and every line would be where there'd be a black spot. That color wouldn't get through. So the colors it gives off are the same as the colors it absorbs. The color it gives off is the same as the color it absorbs. So there's got to be something about the atom that change places. It can either give off that much energy or it can absorb that much energy. But all the other ones it can't absorb. It can only absorb where there's a line, and it can only emit where there's a line. None of the other energies are possible. That's how it's not like a ladder. Because going towards the blue end is going towards more energy. But this element's electrons will never have that much energy. That's why it's black there. Its electrons will have this much energy, or that much energy, never in between. Those lines are what they really saw that said it had to be in energy levels. Okay? So the opposite would be, there'd be a line here, rainbow, rainbow, line, rainbow, rainbow, line, rainbow, rainbow, dark line, rainbow. So the absorption spectra, everything's in exactly the same place. It's just the opposite. You see color where it's black and black where the color goes through. Because it emits those colors when you heat it up, it gives off those colors, but it absorbs those colors when you shine a light through it. Right with that? So, this is what we start with. Okay. Electrons, that apostrophe shouldn't be there. Ooh, it's not possessive. It's not plural. Or it is plural. Electrons start with the lowest energy they can have. And on the ladder, when do you have the least amount of energy? While you're still standing on the ground, right? That's when you have the low. If you start climbing the ladder, you got more energy. Fall off, you'll find out. Okay? So this lowest energy is called the ground state. Just like on a ladder, you start off on the ground. For an atom, the electron starts off on the ground. And go. And I'm not going to get there. We're going to come back to this on Monday, but we're not going to have time to get through it all. But I want you to get the big idea, and then we'll go through details later. So don't worry about copying this down. You'll see it all again tomorrow or Monday. But there's a ground state. This is hydrogen because it's only got one electron. We say we heat it up, it jumps up. Right? Once it's up there, it's going to fall back down. And when it falls back down, it gives off light. But it could fall back down in steps. And each one of these steps would be a different amount of light. It could fall from the 6th to the 4th without being in between, and then from the 4th to the 1st. Okay? So, that's why you see the lines. The fall from here makes the blue line. The fall from here makes the green line. The fall from here makes the orange line.